Thanks, Anna. I really appreciate it. And I also want to thank Sea Grant and also the other speakers in the series for allowing me this opportunity to speak with everyone, but also for letting things get rearranged a bit as earlier in the year we welcomed our third child. As a father, I have to show pictures. So our third child right there, Juniper, is just turned 3 months old, and she was born early and teeny tiny, and so she's finally newborn sized at 3 months old. But it has made the last few months very crazy with two other ones you can see there too. So Hazel is now 5 and Brandon is 2.5. For perspective, all of this started before Hazel was born, when I was at SUNY Plattsburgh, and so it's been kind of, it's all been going on for her whole lifetime. So we've been fortunate to have had support from Sea Grant to do a bunch of monitoring in Lake Champlain to assess kind of impacts of climate change and weather, and also how those things impact the chemistry and biology, which I'll mention briefly in a second. So definitely want to say thank you to Sea Grant, but also this has been kind of it takes a city or village to raise a child. Well, it takes a whole community to undertake these observation campaigns. And so many thanks to all the folks that are listed here. I'm sure I forgot some folks here, in particular Tim Myhook and Luke Myers from SUNY Plattsburgh, who were instrumental on deploying all the data buoys and still are doing it thanks to some their own initiative and also some additional support. And Tom Manley, who I worked with Tom on another Sea Grant project, or on a Sea Grant project, where Tom was just fantastic in sharing his expertise and also allowing a lot of things to happen that would not able to happen. So thanks to everybody. I like to show this slide, and I've actually shown this slide before in Sea Grant presentations before. But I like to think of the lake system as having kind of these 3 little buckets of things that occur inside of it. So the physical processes, the chemical processes, and the biological processes. And more often than not, we isolate ourselves into one of them. So we focus on water quality, or we focus on the ecology of the lake, or we focus on kind of the temperature and the ice and the currents, those things. But in reality, all those things are coupled together, and the physical aspects influence both the biological things and also chemistry too. And so the cycle, and really to understand what's happening in the lake, we have to understand all these different processes. And what we've been doing over the last few years is trying to improve our understanding of the physical side of things, and allowing us then to use that information to better understand what's happening with water quality in the lake, and then also ecology. But of course, there are outside stressors that influence all of these, and similarly, they just kind of cascade through. So, contaminants and pollutants from various sources influence water quality, which then influence biology, and all these things then also influence what the temperature is if we change the turbidity of the lake, and all these things are coupled to each other. Invasive species have a similar role in all of this, and of course, climate change and weather change what's physically happening in the lake, which then also influences water quality and the biology. So these external drivers are really important to understand. And what I'm talking about today really is this climate change and the weather, and also just kind of finding out some things that we didn't previously know, because we now have a record of 7 years of data buoy observations from our primary site, which is just southeast of Valcour Island. And so we've been putting out this data buoy since 2016. And again, this is really a lot of work in collaboration with the folks in Plattsburgh, where it was previously, and who are still doing this, and are fantastic people. I can't speak highly enough of the folks there. And so we've been managing this data buoy, and you can see a little schematic picture that I drew of it right there. I'm really proud of that picture. I consider myself a PowerPoint artist. So the data buoy measures water temperature from the top all the way down to the bottom of its location, which is about 50 meters deep at that site. And it measures temperature every 1 to 2 meters. So it's 1 meter for the first 30 meters, and then thereafter it's every 2 meters, which gives pretty high resolution in terms of water temperature, and it measures every 15 minutes. So relatively high temporal and spatial resolution to really understand what's happening in the water at that spot. And on the data buoy itself at the surface, it's also measuring atmospheric conditions with a weather sensor. recording the normal things, air temperature, wind speed and direction, and pressure. So we use just to show off my PowerPoint skills even more. We use a 2-point mooring system, which you can see here, which allows a buoy to stay still and not drift. As you may be aware, the currents in Lake Champlain can be periodically really strong as the wind forcing gets really moving quite quickly and causes currents to move. And sometimes those currents are under the surface and we don't even see them as they move along with the stationing motion. And so the buoy can drift quite a bit. So we have to put quite a bit of weight to keep it still. But we've been doing this now for 7 years, and we've been pretty fortunate in security. Okay, so kind of set the stage for what things were like in 2016. So in 2016, Tim Myhook and I started talking about, what are the things that we want to know about Lake Champlain that we don't necessarily know or don't have resources for. And there's a couple older papers, and of course Meyer and Grundling, which is like the Lake Champlain guide. A lot of those observations were taken by hand, not necessarily continuous, but the continuous observations that we knew of at the time were primarily from Middlebury, from Tom Manley's work in the 1990s. And I just want to show what Tom found back. So Tom had some moorings throughout the entire lake. The one I isolated right here is some data that Tom shared that's from near Valcour Island. And in fact, this is literally less than a quarter mile from where, or maybe even less, from where our data buoy goes in, or the Plattsburgh mooring goes in. And so Tom did this in the early 90s, and it was a really valuable resource because it showed us a lot of the dynamics of what was happening underneath the surface. In particular, Tom had a couple of papers and chapters about the station motions and the importance of them, and it was just fantastic. And so these are valuable observations of thermocline and internal waves in the Sleish. And observations were not collected, however. In the first 10 meters or so, Tom had a subsurface buoy, keeping everything tight, and it, in a lot of ways, that makes things easier. But we do miss that little part in the epilimnion and the top part of the lake there. And so one of the things that, when Tim and I were talking about what we could do, we could try to do something similar to what Tom had done here, but kind of get that top part and figure out what's happening to the surface. The surface is where we think the climate change would happen the most. It's where we think variability happens the most. So, what can we do? And so when we put our 7 years of data buoy on the same plot now, I kind of bracketed there the new information, which is right. Get my laser pointer. Which is right here, new information that we've kind of gathered, and this is new in the sense that we now have the continuous observations now for 7 years, seasonally, so in the field season, but we're now able to kind of continue all the way back up to the surface. And similarly, we can compare a little bit to what we see between the early 1990s to the late 2010s, and we do see some changes. I'm going to put a caveat on these changes in that they're suggestive because we can see them, but not conclusive because 2 years from the 1990s is not necessarily representative of what the climate was at that point, but nor necessarily 7 years. But we do see that in July, for example, temperatures in the last 7 years were warmer in our time period. In July, that's the orange data. And you can see the dotted and the dashed lines represent 1993 and 1994 for July, which is orange, August, which is red, and then green is September. And we put our 7-year averages on top of that. You can see again the green, the orange, and the red. We can see some shifting in what we see, and so in particular the oranges at depth, and in particular up here, we see some movement towards the right, which is, could be indicative of some warming, or it could be variability. We'll talk about that in a minute. August temperatures in the last 7 years are warmer than 1993, but for depths less than 15 meters, they're basically the same. So look at the red lines. The red lines all through here are pretty much the same. And so we don't have that shifting like we did in July. And in September, temperatures in the last 7 years are warmer. the 1993, but there is this kind of outlier where the hypolimnion in 1993 is particularly warm. But both years, epilimnion is higher. So I apologize for it not showing up very clearly. It does on my screen, but not on the display here. But there is shading around each of these. And so the green and the orange and the red dots are each thermistor that we have. And so it's the average over the 7 years for July and August and September. And then there's shading showing the standard deviation of the entire time period. And so you notice, for example, that the 1993 time period for July from Tom's observations is it's completely more than one standard deviation away from what we observed in our time period, which is a pretty little interesting result. Another point of reference, just kind of to show how things are similar or may have changed. I cropped out and then terribly drew on top of this graph from Meyer and Grundling. So this is observations that they collected in 1972 based out of Plattsburgh. And you can see their red line there is Valcour Island Station, which is pretty close to where we are talking about with our Valcour Island. And you can see that the profiles are similar but different. So I zoomed in to the top 30 meters, which is where they were looking. And you can see our surface values are a little bit warmer. And again, this is one day. So in 1 year from 50 years ago now. And so the comparison is interesting, but what we can glean from it, not necessarily sure. So our data not only allows us to, because we have all this data, not only look at just the temperatures, but we also can look at the thermoclines too. And so what we did is we went through and basically calculated the average thermocline. And again, this is information that we think we have a pretty good definition of. We know roughly where thermocline is in Lake Champlain. We can go out and measure it every day. But what is the average condition? What does it look like? What's the seasonal progression? We know it gets deeper throughout the season, but what are the exact numbers? And so here's what we see with that. So the dashed horizontal lines are showing the average thermocline depths for July, August, September, and it gets progressively deeper as we would expect. But we're putting extra numbers on it now. So so it's not just going to be kind of it's probably around 20 meters on average. And obviously there's a lot of fluctuations around this. We know from the SAICH and forcing, but this is a real some hard numbers on it. So for a point of reference, Meyer and Grundling said for Valcour, where we're talking about, they estimated for the entire field season that the thermocline was 20 to 30 meters in 1969. And again, what does the comparison really mean? It's hard to say, but it's there. I do want to also point out our ability to look at a little bit of June and October as well. We don't have as much coverage in June and October as we do for July, August, September, just because the instrumentation has to come out before weather turns and once weather gets good in the spring. And so the blue shows June, and the purple shows October. And I also want to put down here some observations from our anemometer. And so if we focus on the north-south wind, which is the part that really gets the lake moving, the lake has a north-south axis to it. And so when it's really blowing strongly in the north-south direction is when the SAICH gets excited and everything happens. And in particular, and it's going to come up again in a minute, so keep it in mind, we can see that the average wind speed for July, August, September is roughly the same. I mean, they're different, but they're roughly the same. But the big difference is in the standard deviation. And that standard deviation really comes from storminess, or the degree amount of storms. And that's kind of where September kind of loses it. And so we're going to see in a minute that we see some really interesting things that we can pull out of the July and August data. And September is trickier because of that storminess. It's another factor that we have to worry about, something that we're currently working on. Okay, so let's take these 7 years and look at now, not the full profile, but let's look at the 1 meter temperature. So our top sensor, what is it measuring throughout the year? And you can see just absolute tremendous variability. So starting with dark purple in 2016 and then going all the way up towards yellow in 2022, we can see a lot of change from year to year in terms of offset from year to year. We'll talk about what causes that in just a second. But also just, the daily cycle of up and down. You can see that quite clearly. And so there's a lot of variability in here. And, if we look at how we can diagnose what that variability is, one of the things that we do is we basically just look at the spectrum of the data, or the temporal spectrum of the data, and try to pull out what time scales are important. So at what time scales, how frequently those oscillations occur. And that's kind of what's showing here. And so, look at the winds. There is a daily cycle in the amount of winds that we observe. And so that's going to be what we see right here. So a period of 1 day, there's a nice big peak right here in the wind, but also in the water temperature at the surface as well. Notice it's missing when we go down deeper, so to 20 meters, because the influence of the sun directly, at least, is not quite there anymore. And this is all data that has been had the seasonality removed. So we're looking at just the variation on time scales that are basically less than about 10 days. And so we can see, in the wind, we see a big peak here a little bit after 3 days, which is the hallmark of synoptic or weather occurring. And we see a little bit of a resonance of that in the variability that we can see here. It's a little bit shifted, but it is there. And then everything that we see kind of out in this direction is also just kind of some synoptic or again, weather variability. And it ties in not only with kind of that weather, but also then with the periodicity of the SACE, which is about 5 days in Lake Champlain. And so we can see this big peak right here. And so we're kind of seeing these variations kind of matching up what we would expect. And again, nothing anything novel about seeing this. We know this is happening, but we're putting numbers to it and being able to fully understand it. And so one place that we can take out of this also is we can quantify what it is and look actually what the diurnal cycles is. And again, this is new information about the lake that we didn't have before. And so this is just looking at the diurnal cycle of air temperature for the various months. And you can see, it roughly goes from about -3 to 3 perhaps. And there's a clear, late afternoon maximum, early morning minimum, which is what we expect from air temperature. But we do the same thing with wind, finding that the wind speeds typically reach their maximum in the late morning. And so we have all this information, and we can kind of learn some things from it. And it's nice to have. It's good to know. But when we look at the water temperature, it becomes really clear too. And this actually was a surprise to me, because I did not think that the water temperature at the surface would be as responsive as it apparently is to the diurnal cycle. And so we do see about 0.5 degree of variation in, upwards of about 0.5 degree variation through the various months, which is about 1/10 of air temperature, which makes sense. That's what we would typically expect the scale to be. Water would change about 1/10 of what the air would change. But you'll notice that the seasonal cycle is gone by the time we get to October. And it does extend down to about 10 meters, which again, also was a little bit of a surprise to me. I didn't think it would go down quite as far as it does. So you might be saying, well, so why we do know this? Actually, this is actually important information for any efforts to try to simulate the dynamics of the lake, because this is something that we need to get right. This is one of the major energy inputs and sinks of energy in the lake. And so being able to comfortably understand this is something that we need. Okay, so we have these kind of new information, not necessarily things that are kind of like gee whiz, that's completely new knowledge, but rather things that we've been able to quantify because we've had the buoy in there for 7 years. We're able kind of to start building a climatology of what the lake looks like. And this is important for a number of reasons. One, we want to detect change. And to do that, we have to know what it's like now. And second thing is that we want to be able to figure out variations that happen even on shorter time scales. So not necessarily climate change, but also on shorter changes due to weather patterns like the synoptic variability that we saw here. That synoptic variability, the movement, the currents in the lake are really what can cause there to be stagnant water and algae blooms. They literally move zooplankton around the lake, and so all these things are happening on different timescales. But taking a step back, the warming is the kind of one of the things that we wanted to tackle the most. And so again, when Tim and I were talking about things we wanted to know basically, is the lake warming and by how much, and can we predict where it's going to go in the future? And typically predicting, the climate change in a lake is difficult because the lake is a very small scale feature compared to the global climate that we typically simulate future changes in. So we use global climate models typically, and it's possible to use a regional climate model or to downscale information down to the scale of a lake. But even then, you have to have a lake model to understand it, and it's a very great way of going about things, but it's also a very difficult and time-consuming effort. And so we went a little bit different tact here, and so what you see on the screen now is the warming in the lake, or in the basin, excuse me, since 1880, which is when records began. And so it's kind of some notes there on the side. Oh, I forgot to mark it. So the red is data that has been homogenized. That means that it's data that has been altered only to the extent that if something doesn't make sense, it is homogenized with local records, other local records, whereas the blue is the raw data. So it's what you would get just looking at the thermometer. And there really isn't too much of a difference between the two, but I just wanted to put that out there. So largest trend in the basin, and this is now an average that we construct using all of the available sites in the basin, and they're now, I don't have it here, but I want to say they're on the order of 30 sites that we can use over the last 150 years to understand what climate change looked like in the basin. Largest trends in the winter and the fall, which is great, but it's also the noisiest. And so that means that when you look at shorter time periods, like the last 10 years or last 20 years, the trend might be there, but it's harder to find above that noise. But look long-term, you can find it. That said, we do know that the warming in the basin, so against the entire Lake Champlain Basin, is about 3 times faster over the last 30 years. This is something we've calculated. It's about 0.4 of a degree per decade. And that's 3 times faster than what we saw over the whole time period before that. And so because of that, more than half of the warming that we've experienced since the beginning of anthropogenic climate change in the basin has happened since 1980. And so it's been a real recent thing. And so we like to think of climate change as a future consequence, but of course it already has happened some. But in the basin, at least, it really started to ramp up in the 80s. And you can see that at the graph. If you look at the graph, you can see 1980 and present day is when some of the largest changes have happened. And so rather than using like a dynamical model, I try to figure out using numerical models what future warming is going to look like. We instead kind of use this formula, which looks a little bit complicated if you're calculus phobic, but I promise you it's not complicated as it looks. So the key here is that if we can find a lake water to air temperature to air temperature relationship, so we can find out that they're related to each other. So when it's warmer in the air one year, it's warmer in the water that same year, and find some like relationship between those, not some randomness. If we can do that, we can basically figure out what this value is right here. And this value really it's the sensitivity, or it's how, so if air temperature changes, how sensitive is the lake water temperature? Is it going to change a lot or a little bit? And that's what this is showing us. And if we know how much our air temperature is predicted to change in the future, we can then use those two things together to project what's going to happen in the water. And this is a version of something called statistical downscaling or statistical forecasts, where you basically use observations as an empirical information to then take some other information together, rather than having to go, like I said before, all the effort and all the complexities of using dynamical models to figure out what we're going to find. So now that we have 7 years worth of data from our data buoys, we can kind of look and see, well, do we have a relationship? Can we figure out what that relationship is? And I previously have done this before. You might have seen my talks before where I did this using the long-term monitoring data. And at that point, we found a value of about 0.7. What that means is that for every 1 degree that the air warms, the water warms about 0.7 of a degree. So 7/10 of a degree water, 1 degree warming in the air. So if we look at what we're seeing with our data buoy observations, we can see some pretty interesting and convincing relationships, in particular July. So August and September are statistically significant, but not as significant as what we see in July. In particular, you can see the numbers that we find here are about 0.83 for July. August is smaller at 0.3, and then September is 0.9, but September really is quite a little bit more of a scatter shot. So July is really the one that I think we can focus on the most. And so we can use these sensitivities. Again, the way to interpret this is, and I'll focus on July, the way to interpret this is that if we have 0.83, if we have 1 degree of warming in the air, then the water has warmed by about 0.83 degrees. And what we can do is look out into the future and think, well, how much warming do we expect there to be? Well, if we kind of think of the hallmarks that folks put on for climate change, usually it's 1.5 degrees of warming or 2 degrees of warming as kind of like our oh no, we don't want to go past those thresholds. And we're getting pretty close to 1.5 degrees and 2 degrees. So 2 degrees is our, like, we definitely don't want to go by it. We don't want to have 2 degrees of warming around the globe. Again, these are global averages, so 2 degrees averaged over the entire planet. We don't want to have that because of all the irreversible climate effects that would occur. And 1.5 degrees is our ambitious goal to try to minimize the impacts. And if we do that and look at, like, what does a 1.5 degree warming look like for the basin's air temperature? So 1.5 degrees of global warming means in the basin about 2 degrees warming in the air. Where we live, our latitude where we live, we're a little bit more sensitive to climate change than the global average. And so we see about 2 degrees of warming there. And similarly, this is about 3 degrees. And so if we have the worst case, not the worst case, but we pass that 2 degree threshold that policymakers and scientists and activists talk about all the time, it probably means for the Champlain Basin about 3 degrees of warming in total. Using our formula, we can plug those numbers in. This is what we're projecting, right? And so what this means is that 1.5 degree warming threshold, a 2 degree warming, how that translates into Lake Champlain temperature, surface temperature water, surface water temperature is about 1.6 degrees of warming if it's the 1.5 degree warming, and about 2.5 degrees if we get to global 2 degrees sea warming. And so again, using the long-term monitoring data, we found about 0.7, and so 0.83 versus 0.7, those are different numbers to be sure, but fairly close to each other. All right, so this is new knowledge, new application, new things that we're doing with the data buoy observations. And as we collect more, we're going to be able to do even more differing tasks, different ideas. But I do want to say one of the things that's also new this year is that Lake Champlain is now being included in something called the State of the Climate Report. So every year, the American Meteorological Society puts out something called the State of the Climate. And this is basically scientists go through the last year and try to figure out what is happening around the world in different parts. So in ecosystems, in lakes, like warming of the lakes, and what's happening in state of the climate, everything you can think of, ice cover, storm events, all those things. And this year, our observations from data buoy will be in that state of the climate, kind of adding Lake Champlain to one of the many different lakes that get studied. And so what you see here on this graph is basically the anomaly from 2022. What that means is each dot you see there is a different lake, and the color, if it's more red, means it's a lot warmer than normal. If it's more blue, it means it's a lot colder than normal for 2022. And if I zoom in to find Champlain, it's right there. And observations that you see on here are actually from satellites. And so it's the lake water surface temperature as diagnosed from a varying satellite. And so for Lake Champlain, there are satellite observations that go back into the mid-1990s. And so this is something that we're beginning to use to also inform our understanding of the variation from year to year. And in this report, then there's also the in situ, or the observations on the ground. And you can see Champlain's, our data series is really short, because we only have 7 years, compared to like the Great Lakes, which have 30 to 40 years of observations, and some of the other large lakes around the world. But you can see our record is starting, and hopefully we can continue this monitoring and keep building out that record. I also want to put right here, this is a graph that was shared with me by Laura Carrara, who's the person who's organizing all of this. And what she's plotted here basically is the long term, so from 1995 to 2022, not to 1993, no, 1995, that's a typo, June 1995, average. And that's what this line is showing here. And then the standard deviation is the shading around it. And then our data buoy measurements are right here as a point of comparison to ground truth those observations. And you see the difference here. So the satellites have a little bit of a cool bias, but relatively pretty good throughout the seasons. Okay, so I want to say just one more thing, and then we'll break here, which is I talked about, okay, here we can see September wasn't the best, July was pretty good, and July is pretty good partially because if I go back a few slides, remember the winds, July is relatively calm for the most part, so we do have mixing events, right? We do have strong winds that can cause the SACE to occur and kind of confound what we're seeing. But a lot of the temperature change really is due to just sunlight coming in and the lake cooling itself through infrared. And so if we go, and look in September instead, really the most important thing there is going to be the weather, as it pushes the water around and causes things to mix. And so one of the things that we've been doing is trying to predict this in September, and basically to build models that understand, what is the threshold wind speed that causes this mixing to happen, and is that changing? And this is something that we're working on right now. And so, as it says here, storms and wind make the lake move. And what we're looking at now is there's a way to automate or to figure out when that happens and how strong it'll be. And we've had a decent success at doing this by decomposing it into the ways that the temperatures vary. And so this is a kind of a complex slide just to walk through real quickly, but to show that that we're looking at the structure of how our temperatures vary in the lake and what predicts it. And in particular, you can see this is showing the relationship or the correlation between the wind. And so the wind is going to be, when it's stronger, it's going to cause these things to happen more frequently. And so you can see, though, that it maximizes with a lag, so going back about on the order of about 15 hours or so, but is statistically significant going back to about 3 days. And so we're looking at kind of the wind that's occurring as causing these mixing events to happen, being some kind of average across this. It's something we're working on right now. Okay, so I see Elizabeth Lee's question here about the Southern buoy data. That is something that I won't talk too much about today, other than say that we're still working on that data. We have a tremendous amount of data that we collected. In particular, Tom kept the current profilers that we had down. So we had a project where we're relating some of these same ideas with then looking at how the chemistry and the biology changed. And we're still kind of mining that massive tome of data that we have. So we have basically an assortment of observations that were collected, as you can see right here. So we're measuring currents and temperature from various sites down in the southern portion of the lake near the Champlain Bridge. Actually, those observations we've now completed them, but we still have a mountain of data to mine, like I said. So what have I told you today? So I've told you we now, because of our 7 years of observations, have some new information about Lake Champlain. Some of it is just kind of refining things that we knew, but putting a number on it and being able to like put a climatology or a benchmark on it. This is what it is. Now we know this. And it's new knowledge because we've now had this window where we've been making these observations. We've also used our observations to try to forecast what we can expect for warming in the lake. And that's something that is, again, new knowledge and uses a straightforward method to understand what future warming will look like. And then what's still coming is analyzing what's happening, and what in a lot of ways is what's complicated, is analyzing what's happening as storm events move through. And this is something that we're still looking at to understand what's happening with the temperature structure, but also the currents in the lake and then the resulting impacts. So with that, I'll say it's more coming. But with that, I think my time or so is just about up, and I'll say thank you. And I'm happy to take any questions and chat about any of these issues. Thanks so much.